12.1 Tangent Lines. Okay, we're going to start off here with some vocabulary. Lines that touch a circle at only one point are called tangents. Now, this is related to our tangent ratio that we learned about back in Chapter 8, but it is different. So, a tangent to a circle is a line in the plane here, line AB, that intersects the circle at exactly one point. The point where they intersect, right here, is called the point of tangency. That one should be pretty easy to remember. And we can use previous terminology here, like ray BA is a tangent ray, and segment BA is a tangent segment. Okay, so a tangent is a line, but it intersects a circle at only one point, called the point of tangency. All right, let's look at our first theorem here and see what it is. Our theorem says that a line is tangent. If a line is tangent to a circle, then the line is also going to be perpendicular to the radius at the point of tangency. So we are told that line AB is tangent, and if that is true, and we have our radius here that goes from the center to this point of tangency, then we can say that these two are perpendicular. So now none of our theorems are named here, so let's write them out short. If a line is tangent, then it's perpendicular to the radius. All right, well, what does that help us do? Let's look at our first example. It says that segment ML, so we find ML, and segment MN, so we find segment MN, are tangents to circle O. Okay, so if we look here, we know that these two lines are tangent. Here's our point of tangency, and look at that. We have a radius coming out, and we can draw a radius anywhere on our circle. So we know that a tangent line and a radius are going to be perpendicular to each other, and we want to know what is the value of x. We are looking for the measure of angle M there, LMN. And we see that we have a quadrilateral, and we simply sum all of those. We know that quadrilateral angles sum to 360, and we can solve for M. The measure of angle M is 63 degrees. All right, pause the video. Oh, no, wait, sorry. We have another example. The CN Tower in Toronto, Canada has an observation deck 447 meters above ground level. That's probably important. How far is the observation deck from the horizon? So when you look out, you can see the horizon of the Earth, especially when you're up high. And so how far can you see exactly? And we are told that the Earth's radius is about 6,400 kilometers. All right, so we want to make a sketch here, and our sketch is not to scale. And our radius of the Earth is in kilometers, but the height of our observation deck is in meters. So we want to change our meters to kilometers. Now you could keep it at 0.447 if you'd like. That would be a little more accurate. So we draw there's our tower there. And we are told that the radius of the Earth is 6,400 kilometers, and this is also a radius. So what we see here, if we're looking down from the tower, we get to a point here where we can't see any farther because we get to the horizon. We get to where the Earth curves. So if you have this tangent line, because we are looking here at the point of tangency, we know that this is going to be a right angle. And what we end up with is a right triangle. Okay, this is what we're looking for over here. We know that this is 6,400 kilometers, but how long is this piece here? Well, it's our radius plus how tall our tower is. And this is exactly why everything needs to be in the same units. Now we simply add those together, 6,400.45 or 447. We like to keep things more accurate. And we put that into our Pythagorean theorem. We use our Pythagorean theorem here. That's pretty common for us now, and we seem to be missing a couple of spots. So segment or length of CT, length of TE, so that means this is CE and CE. And we simply plug in and we get that from the tower to the horizon is about 76 kilometers. You can see pretty far. All right, now pause the video and go ahead and do this example. Okay, in our first problem here, we are told that segment ED is tangent to circle O, and we want to find the value of x. We know that a tangent is perpendicular to the radius, so we know we have a 90-degree angle. Triangle angle sum theorem gives us x is 52 degrees. So we found that angle right there. That one was easy. All right, problem 2. What is the distance to the horizon that a person can see on a clear day from an airplane 2 miles above the Earth? The Earth's radius is about 400 miles. Okay, so both of our units are equal. The best way to start this is to draw a picture. So it's very much like the tower that we just drew. We have our Earth here, and the tower sits, or the airplane sits 2 miles above the surface, and we are looking down here at the horizon. And we want to know how far can we see from the airplane to the horizon of the Earth. Well, we simply have a right triangle, so we draw that out, and we label all of our parts. And our hypotenuse here is the radius of the Earth plus the 2 miles that we're above the Earth, and we used Pythagorean theorem. And x turns out to be 126.515, so you can see about 126.5 miles. Now, it's not all that much farther than the tower that's not even a half a kilometer above the Earth. That's because the Earth is very large, and so the curvature is really negligible in the difference between 1/3 of a mile and 2 miles. All right, those weren't too bad. Make sure you draw your pictures and label everything. That will be very helpful. And lucky for us, these tangents make right angles, make right triangles. All right, next theorem. This theorem says that if a line in the plane of the circle is perpendicular to a radius, I see a converse here, then the line is tangent to the circle. So again, because we don't have any names for these, let's write them out. If a line is perpendicular to the radius, then our line is tangent. Then it is tangent to the circle. All right, so that is very much a converse of what we just did. Let's look at our example problem here. We want to find the radius. We are missing a radius. So I see a right triangle, but now how long is this hypotenuse? Well, we are going to add those two. So our hypotenuse is x plus 8. But you know, in math, if we're using a single idea, those are going to have to be in parentheses. So when we use our Pythagorean theorem, right triangles, Pythagorean theorem, we are going to have the quantity x plus 8. That's our hypotenuse. And when we square that, think back to your algebra rules here. Squared means we are multiplying something by itself. So you don't simply just square everything inside. This says we are multiplying the quantity x plus 8 times itself. So we get the quantity x plus 8. And then we have to distribute. So we're going to do our rainbow of sharing happiness here on both of those. And we end up with our first one here, x times x, x squared. And then we go from x to the 8, so 8x. And then we do the second term, 8 times x is another 8x. And then 8 times 8 is 64. We have like terms in the middle, x squared plus 16x plus 64. Okay, be careful with those. Now, if you really remember your algebra, you will notice that this is a perfect square binomial, right? We have the square of a binomial, which means it follows a pattern. 2 times the first one times the second one. 2 times x times 8 gives us our 16x. This is 2 times x times 8. And this is 8 squared. So you can either FOIL it out, or if you recognize it, you can use the pattern. Either way, you have to be careful with that. And so then when we get over here, we subtract x squared from both sides. Oh, yay! Our x squareds are going to cancel out on both sides. That makes life so much easier. And then we subtract 64 from both sides, and we are left with a 16x equals 80, and it's simple math, and our radius is 5. All right, go ahead and pause the video and do the next example. We'll leave that there to look at. Okay, we want to know what the radius of circle O is, and we have labeled our radius x, and we know that the line that is tangent is 10. We know it's tangent because that is a right angle there. They are perpendicular. And we know that from the edge of the circle to this outer point is 6. So we get the sides of our triangle here, x, 10, and quantity x plus 6. We use our Pythagorean theorem. We just substitute in. Don't forget we are squaring the quantity x plus 6. And I came over here to the side and I extended it out, did my distributing, came up with x squared plus 12x plus 36, which should not be a surprise because this is 2 times x times 6 and this is 6 times 6. If you remember the pattern, okay, and I subtract x squared from both sides, yay, they cancel, subtract 36, and I get 12x equals 64, do the division, and our radius is 5.3 units long. If you are careful with those, you will do just fine. All right, our next example says identifying a tangent. It says, is segment ML tangent? Well, how do we know if they are tangent? If ML is perpendicular, so if segment ML is perpendicular to our radius, perpendicular, so segment NL, then we will have a tangent. Well, if it's perpendicular, then we're going to have a right triangle. And if you remember back to our right triangle problems, way back in chapter 7 or 8 was where we learned about, is it a right triangle? Well, if the Pythagorean theorem is true, then it's a right triangle. So we simply put our numbers into our Pythagorean theorem. This is a true statement. So therefore, we have a right triangle. Therefore, our line is tangent. We have a right triangle, so we have perpendicular, so we have tangent. Actually, we should probably go through the entire right triangle, which means they are perpendicular, which means they are tangent. We have to be accurate, right? Okay, that is the converse of the Pythagorean theorem, gives us a right triangle, and it's tangent because it is perpendicular to the radius at the point of tangency. I feel proof coming on using those things. All right, pause the video and do the next example. Okay, it says use the diagram from the previous problem and just change the numbers. So I put them in here, drew my diagram, put them in here, did my Pythagorean theorem, and I got 65 is not equal to 64. Therefore, it is not a right triangle. They are not perpendicular, so it is not tangent. Basically, no. Okay, that's not too bad. Our next theorem says that if two tangent segments share a common endpoint outside the circle. So let's look at this. We have two tangent segments, so point of tangency there, point of tangency there, and they have this common endpoint outside the circle. So we're making an ice cream cone. Then the two segments are congruent. Oh, that's fancy. All right. Once again, no name, so let's write this out. If tangents have a common endpoint outside the circle, then our segments are congruent. If they have this common endpoint and they are both tangents, then we can call those congruent. That looks like it's going to be handy. All right, so let's see here. In this figure over here, the sides of the triangle are tangent to the circle. The circle is inscribed in the triangle. Right? We've got our points of tangency here, and we have done this before. Our circle is inscribed in the triangle, and the triangle is circumscribed about the circle. We know those words. So if either of these things are happening, then we know our lines are tangent. So let's look at our problem here. It says circle O is inscribed in triangle ABC. That is just as good as telling us that these lines are tangent. So we have our points of tangency here, and we want the perimeter. Well, what do we know? We have point A here, and these two lines are tangent, and they have an endpoint, a common endpoint outside of the circle, so we can say they are congruent. So if I know this one is 10 centimeters, I know this one is 10 centimeters. Right? Oh, and look here. We have two more tangent lines that have a common endpoint outside of the circle. which means I know that they are congruent. If this one is 15 centimeters, this one is 15 centimeters. And down here, same thing. 1, 2, 3. I guess we should have started there. 1, 2, 3. This one is 8 centimeters. So that makes it easy to find the perimeter. I simply add up all of my sides, and I get the perimeter is 66 centimeters. Okay, well, and look, we have an example or a problem. Pause and do the problem. Okay, this problem said that circle O is inscribed in triangle PQR. That is just as good as telling us that these lines are tangent to our circle. So I marked my point of tangency, and we see here that point P is common to those tangent lines, so I can label both of those 15 because we know they're congruent. Point R is a common point of those tangent lines, so we know those lines are congruent. I can label that one 17 centimeters. And up here, point Q is the common point outside of the circle, can't forget that, of these two tangent lines, so I know they are both congruent. We don't know what length they are, but in math, that doesn't matter, so I called both of those X centimeters long. We know that the perimeter is the sum of all sides. I always write out my formula because we are told the perimeter is 88 centimeters. I substitute it in. I add up all of my sides. I get 88 is 64 plus 2x. X plus x is 2x. I do my opposite operations. I get x is 12. So I'm asked for the length of segment QY. The length of QY is 12 centimeters. Now, that's not too bad. These are really, the concept, once again, is simple, and we are back to where seeing them is the difficult part. So be very careful. Make sure you are drawing and labeling and drawing and labeling and drawing and labeling everything. And again, you know, color is your friend.